Hey, my name is Tim Wormann, and I'm a doctoral candidate for the European High Order Mode Technology Program. So, what are high order modes and why are they useful? I think to answer this question, we're going to go a little bit back and talk about how can light be used in order to transmit information. As of right now, you're actually doing it. So, when you're using the internet, you'll get the information probably over cable to you into your house. Many households in Europe already have glass fibers. So glass fibers are used together with some kind of lasers, and then you shoot light through this kind of fiber, and you can put information into it. You can imagine it like turning it on, turning it off, and have zero and ones. And then you can have the data you want to access and you want to obtain from the internet being encoded into these kind of on-offs. But our internet speed would be really slow if this is our only way of putting information through it. So what we can do is we can use multiple glass fibers, which is being done. But we can also use some other thing. So instead of just using one laser and sending the signal through, we use a second laser, but then we give it another wavelength. So that means another color. Then, in the end, we use some kind of special machine, which is really easy to do, to split off. You can use enormous amount of colors. So we can process the data from these separately, which is really good and really great for high transmission speeds. And what we are trying to do here is using yet another property of light. And this property is called high order modes. And high order modes, you can imagine, are spatial properties of light. So imagine we have laser light coming like this onto us. Don't shoot with laser light directly into your eye, don't do it. But let's imagine it. And what you would see is just a dot. And this dot is called the fundamental mode. So this is like the standard mode of laser light. But you can also achieve higher modes. So then, if you send the higher mode, it's not only a dot, but it's a dot with a ring around it. That would be a higher order mode. So the laser light can propagate actually in such a constellation also. And then we can put them all on top of each other and use some other kind of machine to, in the end, filter out the different kind of modes. So we filter out the colors, we filter out the higher order modes, and we get yet it's what you would call another channel of information stacked on top of each other, and thereby we can increase transmission speeds. Here at KTH we do something which is called mode conversion in free space. So let's imagine we're not sending the high order modes through fiber, but we're sending it through air. Where is this being used? For example, in Wi-Fi, or we have internet connection through satellite. We also have it in certain measurement techniques where satellite send out some laser light in order to detect certain air particles. That's why it's really important to be able to convert these high order modes from one color to the other. And here at KTH, we use special crystals for these, which are called backward wave optical parametric oscillators. And here we can see a BWOPO in live action. The material we see here is potassium titanyl phosphate. It doesn't look that special at first glance, but it will show all of its crucial details once we will put it under the microscope. So this is what we're going to do now. We are employing a magnification of 100x here, and the computer yields us the results we were yearning for. These small black lines are periodic structures called polling periods. I'll show you a better view in this picture right now. These have a size of around 500 nanometers, which is roughly 100 times thinner than a single human hair. Crystals with these polling periods are really challenging to fabricate, but allow us to convert light into the desired colors. When we send infrared or laser light through such a crystal, we can split all the colors up through a special optical grating and get lots of rainbow colors appearing on the screen. These are some of the converted colors we want to see. And there's much more invisible light being created, which is much more often employed actually in applications later on. We now use special optics like this conical lens here to create higher order or even more intricate beams to use with these BWOPO crystals. I hope you got some insight and some idea on what has been happening here at the Royal Institute of Technology in Stockholm for the High Order Mode Technology project. If you're interested further, I would like to advise you to visit the website and also check out the videos of the other doctoral candidates. But with any further ado, I would like to thank you for your attention, and I would also like to thank for the ongoing support for this kind of project.